today we're going to look at how do you solve the motion of an object accelerating along an incline. And this is hard, like we said, because your speed is never the same, right? We have acceleration. Also, there's motion in both the x and y direction. A skater on a half pipe will go left to right as well as up and down against gravity. The other thing that's tricky, as you can tell, is there's friction in this case, right? Because ideally, if you start at 10 feet off the ground, you should return to 10 feet off the ground. But in real life, because of friction, a lot of the energy is lost to heat in the end. And that's just part of real life. But also in a half pipe design, it's designed so that when a skater wipes out, they can safely dissipate their kinetic energy to friction as they slide down that hill there. And that's something a half pipe designer has to take into account. So the little trick we're going to use, and here's another kind of cool simulation here, and let me just clear it out here, is if you think about it, when you're trying to push something up an incline, it gets a little bit complicated because there's a bunch of forces acting on this object. You got your applied force, you have the force of friction opposing you, you have the normal force of the incline, the ramp supporting you, and then you got a pull of gravity going straight down. But the trick is you don't think of x and y anymore, up, down, left, right. You think of tilting your reference frame in terms of what matches the incline, what's going parallel and what's perpendicular. And that's just the one little trick we're going to use. It's not going to be too bad. So a couple things about Tony Hawk I had to look up here. He is 6 feet 3 inches tall, but the big thing is we just need to know his weight. It's 170 pounds. So really quick, how do you convert pounds to kilograms? So all we got to do to convert pounds to kilograms is you take 2.2 pounds in every kilogram. And actually, we have pounds, so we don't want to multiply. We're going to do what? We take 170 pounds, and we just divide by what? 2.2 pounds per kilogram. If you divide by 2.2, so roughly, your mass in kilos is your weight divided by 2. It's 2.2 to be a little bit more precise. It's about 77, round that off to 77 kilograms. So for our little example, we're going to use Tony Hawk's mass to be 77 kilograms. And here's what we're going to do. We're going to do a sample calculation for what somebody who's designing a half pipe would have to do in order to not injure somebody, an athlete on a half pipe here. So we're going to use the fact that his mass is 77 kilograms. And here's the basic idea. When you're on a half pipe, the trick is, the thing that makes it a little bit tricky is you're on an incline, right? And let's just pick some. The incline was really steep. It was actually 90 degrees at the end. And then as you go down, it actually tapers off. But we're just going to pick a section where we're just going to set it to be constant, not have it change. So why don't we pick an angle? I don't know. How about 60 degrees? That's a pretty steep angle for the incline here. And then we're going to look at Tony as he's going down. And specifically, why don't we look at the part when, because here's what's kind of interesting. When they fall off the skateboard, did you guys catch how they lose the energy there? Yeah, the skateboard's like flying down here, right? Which has a very low coefficient, maybe only 0.1. But they're actually sliding like on their knees, which I don't really know how to draw exactly, on the knee pads there. And as they slide down, that frictional force is what brings them to a safe stop. So we're not going to even worry about the skateboard. Let me get rid of that. And what we need to know is a couple things. We need to know his mass, which was 77 kilograms. And we also need to know how fast he's going to accelerate down that incline. So that's our ultimate goal. We're going to figure out if Tony Hawk wipes out and he's sliding on a 60-degree incline, how much would he accelerate down that incline because of the pull of gravity? And then that's something that a half-pipe designer could use to adjust to make it safer. Because you don't want them accelerating too fast, they're going to get injured. But if you make it not steep enough, it's really lame because they don't do cool tricks then. We need to know a couple things. The first is we got to figure out all the forces acting on Tony Hawk here, right? So let's go ahead and think about the forces. What's the force that always acts? You got the pull of what? Gravity that goes which way? Down. So the big thing to realize is gravity always pulls down. People get confused and they think, oh, it starts to pull sideways down the ramp. It doesn't pull sideways, but we're going to break it down into two components later on. What else acting on Tony Hawk here as he slides down the incline? We have the normal force. That's correct. Which way does the normal force work? It works perpendicular to the incline. That's important. So you got to remember, normal means perpendicular. This is a 90-degree angle to the incline there. What else? There is the force of friction, which is which way? It's going to be opposing the motion because he's going down, right? He's sliding down. This is the force of friction. That's correct. And we only need to know one more thing, because if we're going to find we're going to find acceleration. That's our big unknown. That's our goal. We need to know force of friction is equal. Remember the friction equation? Friction is what? Fun, right? Yeah, the force of friction equation is it depends on the coefficient of friction and then how much the surfaces are pushed together, the normal force. So we need to pick a coefficient. And I actually went online. I was trying to research this, and I was going to all these skater sites. They don't really know offhand. So roughly, wood on wood is anywhere from like 0.1, there it is, or sorry, 0.25 to 0.5. And the ramp there, the half pipe, was made out of wood. It was a fancy kind of wood. But they're sliding on their knee pads, which is like plastic, so it's pretty slick. So why don't we say it's, instead of, well, that's static friction. So for sliding friction, it's 0.2. Why don't we say it's a little bit more slick, plastic on wood? How about, I don't know, 0.15? It's pretty reasonable, right? We're going to set the coefficient of kinetic friction, or sliding friction, same thing, of knee pads on wood to 0.15. And believe it or not, we can actually figure out then how fast is he going to accelerate down this ramp as he slides. We can actually figure that out. Now, here's a little trick we're going to use on our free body diagram. I'm going to zoom in here. And that is, we want to think of everything from the point of view of the ramp. We're going to tilt our frame of reference to match that incline. We're going to tilt our heads. We're going to think of everything as either perpendicular to the ramp or parallel to the ramp. So notice the normal force is perpendicular to the ramp. The force of friction is parallel to the ramp. So the one that doesn't work for us right now is which one? The weight vector. So here's a trick. Don't think of gravity as pulling you straight down. Think of it as doing two things. Remember how every vector can be broken up into other vectors? We're going to break this into a triangle, a vector triangle. This is a right angle. This is going to be called weight perpendicular and weight parallel. So in other words, gravity is doing two things. This is a right angle. Gravity is pulling you down the ramp, down the half pipe rather, and then it's also holding you onto the ramp. You see that? So in other words, if you want to go snowboarding, right, or skiing, is Chicago a good place to go snowboarding or skiing? Not really, because it's pretty flat. It's boring, right? You go to places like what? Yeah, you go to Colorado, maybe go to Vancouver, go to Whistler, because on a mountain, there's a big old incline, a ramp, right? And part of the job of gravity is to pull you down that hill, that ski hill, that ramp. You're going down the hill there. And then part of its job is to hold you to the mountain. If there was no gravity, it wouldn't really work very well to go skiing and all that, right? So by the way, when you go skiing and snowboarding, you're not paying for gravity. That's free with your subscription to the planet Earth. Welcome, we come in peace. But what do you literally have to buy? You have to buy a what? To buy a lift ticket, right? Because it costs money to run the motor and the electricity and the gas and whatever to run that lift to get you to the top of the mountain. So literally, when you buy a lift ticket, it's legit. You're paying for the energy to run that machine, to lift you to the top of the mountain. But they shouldn't charge you for gravity.